welcome to this tutorial, guys, on numerical differentiation. We will be going over the forward, backward, and central difference formulae, as well as some examples on them. I won't be going over the derivation of these formulae. I'll just be stating them and then showing you how to use them. Okay, so let's get into this. Okay, so essentially with numerical differentiation, we just want to find a numerical method instead of an analytical method to differentiate a given function. Okay, so let's get the formulae down. Okay, so for the forward difference method, the equation is f of x plus h minus f of x over h, where h is your step size. Okay, for the backwards, we have f of x minus f of x minus h over h once again, and these both have an error or order OH. Okay, we'll speak about this a bit later. And we have f of for the central difference, we have f of x plus h minus f of x minus h over 2h, so a bit of a combination between the forward and backward. Okay, so this has order of OH squared. Okay, so these h's are just your step sizes. The x is the value at which you want to differentiate the function, and these orders tell us how good the estimate is, the order of accuracy. With numerical differentiation, you will not get the exact value of the derivative. So as our h decreases in these formulae, as h goes down, our accuracy goes up, and as the squares, so as we get higher orders, or as we get to h squared, h cubed, h4, our order of accuracy increases. So we want to have a higher order of h for more accurate answers. Okay, so let us try an example, and let us try an example which is, let's go for x squared cos of x. Okay, so let's say we want the derivative at x is equal to 2, and we want step size h equals 0.01. Okay, so using the forward equation, we can say, so everywhere that I see x in this equation, I have to insert x plus h. Okay, so let's go over this. It's going to be 2 plus 0.01 squared cos of 2 plus 0.01, and then it's just minus f of x, which is just going to be 2 squared cos of 2 over h, which is 0.01. Okay, and the value we get for that is minus 5,333,933,817. Okay, so we do have to keep this fairly large number just to see how accurate our answer is. Okay, going on to the backward difference, we have f of x first, so we have 2 squared cos of 2 minus f of x minus h, so we have 2 minus 0.01 squared cos of 2 minus 0.01 all over h, once again 0.01, and the answer that we get is minus 5,2695,1445. Okay, and lastly we have the central difference, so we have f of x plus h, so we have 2 plus 0.01 squared cos of 2 plus 0.01 minus f of x minus h, which is 2 minus 0.01 squared cos of 2 minus 0.01 all over 2 times h, which is 0.01, and the answer that we get is minus 5,301724,134. Okay, so as we can see, we always get slightly different answers for each one, and we know that the derivative actually has a single value. Okay, so because this is such an easy function, we can actually differentiate it using the product rule, and we will get 2x cos of x plus x squared minus sine of x. Okay, and if we plug x is equal to 2 into there, we get a value of minus 5,301,777,053. Okay, so this is the actual value of the derivative. Okay, so let's compare these now. So both the forward and backwards lose its accuracy roughly after the first decimal point. But if we look at the central, we actually have about 4 decimal points worth of accuracy, which is what we have here, where we see that both of these are the same order and this central difference is of a slightly higher order accuracy. So we should use the central difference if we want accurate answers. If we want a quick estimate, we can use the we should use the central difference if we want slightly accurate answers, and if we want a quick estimate, we can use the forward and backwards. Okay, so the question is, why would we use this somewhat long method when we can find the derivative? Well, there are cases where, such as this function here, where we can't actually quite easily find the derivative. It would be quite tedious to carry out this derivative, so it might be easier to just run a numerical method. Okay, so let's go with the central method, and we have an x equal to 2 at x equals 2 and h is equal to 0.01. Okay, so I'm going to use the central difference method. Okay, this is quite a long one, so bear with me, guys. So we have 2 plus 0.01 squared ln of 2 plus 0.01 cos of 2 plus 0.01 minus 2 minus 0.01 squared ln of 2 minus 0.01 times cos of 2 minus 0.01, and that is all over 2 times h, which is 0.01, and the answer that we get for this is minus 4,7270522. Okay, then I went ahead and I plugged that function into some software and got the actual derivative analytically as well, and the analytical solution is minus 4,507,205,497. Okay, yet again we have 1, 2, 3, 4, so we have about 4 decimal places of accuracy. Okay, so yeah, that's basically what I wanted to run through in this video, just running over the formulae and how to use it with some examples. In the next video, I will be covering Richardson extrapolation, which gives us a slightly better order of accuracy, but it is a bit more tedious. But thanks for watching, guys, and I hope you found this useful.